Ooh, hello everybody. Hello. Welcome to ML Monday week 6. It's been a while since my last ML Monday. I hope you all have had a wonderful couple of weeks. I put a lot of time into this one, and I hope you all are able to learn something new today. That's always my goal, is to help you guys learn something new. It's week 6. So the agenda for today is, also, by the way, there's links to stocks and cryptocurrencies in the video description that you should go download into files. You can just throw it into the resource. So there's also the GitHub. Don't forget about the GitHub. You go to lectures, week 6, and you can see the code that I wrote for us today. I'm still working on it. But it is working code. It's just, it might not be the most efficient code for what we're doing. I didn't have time to do some hyperparameter testing or whatever. But yeah, so our agenda for the day, we're going to start off talking about what exactly time series data is. After that, we're going to be talking about how we can download. Oh, Brett, thank you for becoming a GAITOR. Welcome. I like it. After that, we're going to be talking about downloading stock data, how you can do that, where you can go to Kaggle and download a bunch of stock data. Then we're going to talk about an introduction to APIs. And then after that, we're going to be talking about time series forecasting, which is the actual event for today, what you should be learning from. We're going to spend about 5 to 10 minutes on time series data. If you guys have any questions about it, this is very important. Time series data is very common in many applications for machine learning. Then we're going to talk about downloading stock data. I'm just going to give you like resources, places you can find stock data, cryptocurrency data, etc. Then I'm going to go and introduce you guys to APIs, so you can get live data from servers and stuff. That I'll be doing that. That'll take 5 to 10 minutes. And then finally, for the rest of the time, hopefully we have more, like 40 minutes for this. I'm going to talk about time series forecasting and get into recurrent neural networks and how they work. So let's talk about time series data. Time series data is extremely useful. There's this thing in Python called datetime. It's a library. You have a string parse time where you can parse times. You can put whatever date format you want in there. So if like you have an Excel sheet that has dates in this format, you can just pretty much use this Python thing over here and figure out what correspond to how that date is formatted. Now that we've talked a little bit about that, you can format times into like whatever time you want. And the cool thing about date times in Python is that there is a library called to_datetime in pandas that essentially just allows you to convert it, like automatically finds the format of the date and is able to like give you a date string back based off of what it thinks it is. And then this here, the df.index is equal to pd. So if you changed your index to the date, you can just change that index. This is just how to change your index. What's up, Wes? How's it going? Glad you're in here. Yeah, so to_datetime automatically detects common date formats. And yeah, so that's a very useful tool. So this is datetime in pandas. So a little bit about the datetime object. In the back end, what you guys aren't seeing is the actual time object is just a number counting the milliseconds from January 1st, 1970, which is otherwise known as Unix time. Unix time is pretty much the standard, and this datetime class, it just changes the format of this timestamp, counting the sort of milliseconds from January 1st, 1970. So you can pretty much convert any datetime format that you want into milliseconds from, yeah, big fan of Unix time. Of course, Unix time's the best. Helps out a lot. It's good to have you guys here. And this makes operations, so like this makes things like sorting by time, sort of taking times and adding and subtracting them, making time into an index in your data frame, which we've talked about before. It makes it super easy for your computer to figure out like where time is. So now that we've talked about what kind of time series data is and how you can use formatting to basically use any date format that you want, let's talk about how we can download some stock data. So the place I like the most is Kaggle, because it's already in the format that you kind of like. It's in CSV format, Excel format, SQL, whatever kind of format. But you can also get it from Yahoo Finance, NASDAQ, MarketWatch, TradingView. There's a bunch of different ones that you can sort of access an API to get live stock data. So you can use this in your actual APIs. And so just in Kaggle, I looked up stock data, and there were 926 different data sets just on stock data. And most of the time, Kaggle, it comes in like a CSV, JSON, or Excel format. Most of the time it's CSV, which we've already used many times in our Machine Learning Mondays before. So yeah, what about live data? So what happens if you want live data? Hey, I'm glad you asked. I'm sure you guys are asking about live data. So that's where we're going into an introduction to APIs. So there's three main types of APIs. There's one with no authentication. Yes, live data, live indeed. There's three main types. There's no authentication, there's credentials, and there's OAuth. No authentication is normal. It's like, yes, live data. Emphasis on the data and emphasis on the live. Actually, emphasis on the whole thing. There's no authentication required for these things, and whenever you call the API, it comes back with whatever is in the actual database at that current time, which is super useful, because if you wanted like stock market prediction price predictor, you don't want past prices, because those don't really matter. You want the current prices so you can predict the future current prices. If that makes sense. And so there's also ones where you can have like these credentials. I know GitHub used to use credentials, which is just you input your username and password into a header, and it gives you an API key, or like not like an API key. It's like some sort of key that you can use to authenticate with the server, and that key is updated every time. And there's also OAuth. OAuth is very common. It's become the standard pretty much. And with OAuth, you basically you kind of log in using your API keys and everything, and it gives you like a session variable or a like session ID, and that session ID expires. And it's the most secure type of authentication and is used a lot. And I'm just telling you guys of this so you know what to look up if you guys are using it. So here's an example of no authentication. If you were to just get any URL, so replace this string with a URL string at all, this will contact that sort of endpoint for the API, and it will get whatever data that API sends back, and then this r.json just converts whatever data you got from that URL, if it was in JSON format, into a JSON object that is super easy for Python to figure out what's happening. Okay, and then now that we have a data frame, and we can read the JSON from this JSON object. So say you got like a JSON object from your file or whatever, you can read that JSON object sort of into a data frame, which is super useful. Wes, I know with a lot of trading bots, they have to use API with the best of my knowledge. Yes, so most trading bots, so if you're creating a trading bot, like a live trading bot automatically, chances are you would have a credentials or OAuth sort of authentication where you're able to update your profile whenever, like, say you want to run your model every 5 minutes, just check to see if whether a stock is going really high up in price or really low sort of in price, and then you can kind of predict that, and then if it's going really high, then you buy right before. If it's going really low, then you sell right before, which is incredibly useful. And when I can talk about that more, but I'm just trying to introduce you guys to this type of stuff so you know where to go. And finally, there are pre-made Python packages just for finding stock data. AMC is up 30%. Let's go! Congrats, that's hype. And so there are these pre-made packages that you can get this finance from. And this one that I just found on the internet is called Y Finance. You literally just need to pip install. So if you have Python, you probably have pip. Pip is just a package manager. Pip install Y Finance, and you can import it into your thing and just get any ticker you want. And that ticker is going to have, again, the date as the sort of index, which means that it's indexed by time, aka it's a time series. And the history period is equal to max, so that just gets like however much it's however long it's been like a company, it's going to get all that data. So you can see that this data starts at 1980 December 12th for Apple. Okay, so for the rest of the time today, we're going to be talking about time series forecasting. And yeah, so basically, if you guys have any questions about time series data, hit me up in the chat. I went a little fast on it. I hope you guys kind of understand, Unix time and how that all works. But we're going a little fast. We're going a little faster than I intended, but it's okay. It's fine because I have a lot to talk about with time series forecasting. Literally any time series. You can pretty much take anything. Like if you have weather data, if you have stock data, if you have, say, a sensor data, like any sensor over time, as long as there's a time dimension in your code, this code will work, which is really powerful. So yeah, let's get right into it. There are four main types of time series forecasting. There are, and the first two types are called single time step forecasting. One of them is where there's a single feature. It means that it's trying to predict a single feature through one dense layer. So you have one input and it produces one output. That's a normal, like a regression layer, right? Oh shit, I think this uses live Yahoo Finance data. Yes, so Y Finance, the package that I said before, does do live Yahoo Finance data. So that is an option if you guys want to use live data. Okay, so now that we've done this, let's go to single features. So predicting just one value. So this only predicts one value. If you have, say, t is equal to 1, it tries to predict t is equal to 1, and then its entire loss function is based off of whether or not that prediction was correct. This can be used from a simple dense layer, and one example of this would be only trying to predict the close price of a stock. Okay, and so this is kind of what we like to call like a vanilla neural network, where there's an input, a function, and an output. The function fits these sort of inputs to create the output. And again, these are slides that I found from the Stanford School of Engineering. I'm going to use a lot of these slides. They're amazing. These were created very recently in 2017, and I would highly suggest, I will put a link in the Discord for where I got these slides as well. Very useful. So yeah, very, very recent, very powerful stuff we're going to learn today. So this is basically like a one-to-one relation. And so if we have, say, many features, like we want to predict the open, low, high, and close of and the volume of the entire thing, we can have all these different labels where each label is like a tensor or like an array that we want to output, and then we predict the entire array of outputs that we want based off of an entire array of inputs. And this is one to many. So this one would be, say, like just the close price of the inputs, and then it would try and predict like the close price of the labels, or would try and predict all the close prices. So yeah, this is basically like, instead of just predicting the close price, this predicts many features, or something called like a tensor, something that has like a bunch of different features, where it has like open, high, low, and close, and each thing is considered, each different index in the tensor is considered an independent variable, where they're not sort of related, which in our case they are, but we're going to assume they are not. So after one to many, we have many to one, which is what we're going to start out today coding. And basically what this does is, so for example, a really good use of this would be like a sequence of words, and you want to output, say you have like a sequence of words and you have like an array of these words and how they are weighted. So there's only like a certain number of words in the entire English dictionary, which is, I mean, pretty obvious that there's only like a certain number of words. I think there's only like 700 or something like that. You just have an array that's 700 long, and then have a 0 or a 1 for whether or not it's that word. Except, or you can do something where you have these weights, and you basically take these sequence of words, which is just arrays that have a sort of index of 0 or 1, and you can throw it through a neural network and output something called a sentiment, or like a classification of whether or not it was like a good sentiment or a bad sentiment. And so basically we can do this, but we can also do this on stock data. An example of doing this on stock data would be like having like the last 48 days of inputs, and having the day after be the output that we want to produce, or the labels. These labels in green on this graph here. So there's 1, there's 2, there's 3, there's 4, right there. So this generator, which I will talk about later, generates 48 inputs with a label having 1, and the shift also being 1, which makes it so we basically just have this many to one sort of operation, where the red is the inputs, the blues are the outputs, and we can create this model that has one dense hidden layer, and the hidden layer is what basically helps make it actually functional. And then we have a dense layer of 5, which just outputs the open, high, low, close of this value. So this is pretty useful. We can do a bunch of stuff with this. The example I based this one off of did weather data, and they got a lot closer than I did, because weather data is a lot less random than stock data, but stock data is a good example and gets clicks. So I did stock data. You can also do cryptocurrency data. I will talk about in my code how to import stuff like that. So in my code that I wrote, there's this thing that I have called a window generator, that you're able to basically take any data frame that you want, and you're able to generate a data set based off of however long you want your sort of input width to be, however long you want your label width to be, and however long you want to shift your data. And you can see right here, they kind of visualized it, how it went out. So if we wanted to like have an input width of 6, a label width of 1, and an offset of 1, we would basically just create this generator, and this is exactly what we would do. It's that easy. Now that we've done that, the meaning of this data set is to generate a data set to make a price prediction for one day in the future when you're given the past 6 days of prices. That's really what we're doing, is we're just trying to predict the future based off of the past 6 days. And we'll talk about why that idea means that it's a recursive function, because the inputs determine the inputs determine new outputs, and then those outputs are then create new inputs, which is, we'll talk about that later. I have whole diagrams and stuff. But for right now, we can kind of see that so if we do this model and we show it what it looks like in like the actual terms, where you have the inputs is this blue line, and then the labels, what we want to produce, the output is this green dot. We can create these sort of inputs and output schemes based off of like only the past 4 or something days, and then we can predict like t is equal to, in this case, 5. And so basically that's super cool. A really good way to do this is to actually use convolutions. So this example here was using convolutions, and you can see that this right here, this diagram right here came from this diagram here. We just split it into different parts, where we have this last part. This last part is the actual label, what we want to like predict. These inputs are actual like inputs, what we want to put into the model, and then we can basically just use like convolutions and dense layers to predict these next values. So convolutions, we talked about that before. Convolutions are basically just a way to scale data, or I guess summarize data and produce a meaningful output based off of that data. And these dense layers are simply just regression layers that allow you to sort of fit the data however you want. We're actually going to watch a video later that gives a visualization of how these dense layers fit data, and that's really cool. And so basically, if we create this generator where the input length is 5, the label is 1, and the shift is 1, we can use a model to then flatten the data. So when we flatten the data, we basically take all of the data that we have. So if we had like a 2D array of like the first day being like the open, high, low, close, the second day being the open, high, low, close, the third day being the open, high, low, close, we basically shift those together. We flatten out the array where it's the first day open, high, low, close, and then the second day open, high, low, close, all in the same thing. And we're able to use convolutions and dense layers in order to produce an output that somewhat kind of predicts it well. This is better than the last one. So the last one predicted. So we can kind of produce this one very well. So this one here is a really large input to create one output, and this one here is a small input to create one output. But what we're gonna do is eventually have these same weights throughout the entire model, throughout the entire convolution, and we're gonna guess it a bunch of times, right? So instead of doing this, so let me walk through the code data here. So I have this data path. So basically all we're gonna do is just import TensorFlow, NumPy, pandas, all this stuff. Get our current working directory. If you guys want like to do a stock other than Apple, you can. These are all in there. These are by market cap. I just added that to help you guys figure out which ones you want to look at. But if you guys can't read it, let me know in the chat as well if it looks good. Yeah. So we have this data from Kaggle that I downloaded. The link is in the YouTube description if you want to go download it. It's from Kaggle, so it'll be pretty easy to figure out. And so basically we have all these different stocks, right, of all like the stocks that you could ever ask for in here. And then if we were to look at this actual data here, we can see that we have a date, an open, high, low, close, volume, and then an open int. I honestly don't know what open int means, but we're just going to go with it. Yeah, I can look at this data. So this is what it would kind of look like in Excel, where you have the volume here. We have the close, low, open, high, low. So let me just sort by date, and you can see all this stuff. We have a bunch of data on Apple, and it's by the day. It's by the day, which is important for us to sort of figure out what this data means. And so what we're going to do is with this data is we're going to transform this data. We're going to do something called a min-max scalar. So instead of it using the actual price of this stock, we're going to scale it so the minimum, so we're going to subtract by the minimum and divide by the minimum minus the maximum. So essentially all we're doing is we're just creating instead of it being the actual stock price, we're creating a way to scale the data so it's scaled between 0 and 1, which is a lot easier for our neural network to figure out what's going on. Yeah, so basically I created these functions that just says get stock data. If you wanted a stock data other than Apple, all you would have to do is just go to which line is this? Go to one moment. Symbol. Yeah, all you'd have to do is just go to this actual line right here, and where it says get scaled data. All you would have to do is just change whatever stock symbol you would want in this string, and you just have to make sure that it's in this data set, or that you're getting it from the right API, that your API actually has it, or whatever. Just make sure that this data frame isn't empty, and it has quite a bit of data because we're going to be training it. And basically we're doing the same thing where we just take this fraction where we take like all the data frame samples, and we take like we take 40% for our we take 60% for our 60% of our data frame for the training, 20% for our validation, and 20% for our test. This basically just means like 0.0, comma 0.6, comma 0.8, where like this between 0 and 0.6 is trained, between 0 and 0.8 is validation, and between 0.8 to 1 is test. That's basically what that does. Then we have this class window generator that basically just takes these training data frames and it allows you to input like the input width, the label width, and the shift, which is in this picture right here. So the input width, the label width, and the shift right here, or in this picture it's an offset, where you just shift, and that would be that label width is the actual goes from the back to the front, and the offset goes after the input width, which we're going to see why that applies later and why it's super easy to just use the class to do that. Okay, so yeah, so this class here is for you to use. You can do whatever you want with it. Yeah, so here I put it on the thing already, so oh well. It's fine, it happens. And then we have this window generator. So this was the one, so if we wanted to say make this part in our window generator, we would just do, so this was on the slide, we just create an input width of 6 and a label width of 1 and an offset or shift in this context of 1, and then this shift of 1, and then this label width is like the target, and then this input width is like your X. And then so we create this generator where we have the first 48 indices being the input, and then the last indice, or 48, the last indice being the output, or like the Y. So this is our X's. So like think about it like X0, X1, X2, X3, X4, and then think about this as Y. Okay. And then for each of these outputs labels, we have an open, high, low, close, and volume. And so basically, there's this function called split window that basically just takes all these different windows that we have inside of our thing, and it just splits them into inputs and labels based off of what you put for these values. Input width, label width, and shift. And yeah, it's pretty much that easy. All you got to do is just take like your CSV file and input like however much you want to shift stuff. Okay, and what I did here is I just put examples of like the first thing inside of basically the first thing that can be generated. Then I have the 100th thing that could be generated, the 200th thing that could be generated, the 300th thing that can be generated, the 400th thing, 500th. So we have like six examples of things that can be run, and you can see that our window shape. Like our window shape is 6 by 49 by 5, and our input shape is 6 by 48 by 5, and then our label shape is the like future value or our target. Yeah, so this final dimension 5 would be the open, high, low, close volume for each of these things. So we are getting an input of the open, high, low, close volume for each of these values. And yeah, so we can basically, so this 5 down here is what we would consider a tensor in TensorFlow, where it considers those as like all their own sort of regression values. Okay, so I created this thing that you can basically just take the plot. You can just create an example in here, and then create a plot from these examples, and you can just plot them out by just taking your generator and plotting out the examples thing that you decided you wanted. And here's the example. So these blues are the inputs that you gave the model, and the green is the output that you gave the model, or the target. Let me just unblend this. And yeah, so it's that simple. We have, if you change this value from plot call to close to volume, you can change what's being shown in the graph. So like if I want to like open instead of this is gonna close, but if you want to like open instead of this, then the Y here would be open instead of volume. And yeah, hopefully you guys kind of understand what's going on here. It's basically just a way for you to visualize what's happening. And also in this plot, I made it pretty simple for you to take your model and just put your model in, and then generate your outputs based off your model inside of here as well, so you can just see your predictions right on the thing, which we'll apply later. Yeah, so that's pretty simple. And so I created this function also called make dataset that just uses this time series dataset from array, where it just gets our entire array. It creates a dataset based off of, you know, how all this stuff is. Hey, Mom. Where you can create this dataset based off of all this stuff, where you have the data, the targets, and then the sequence stride in this case would be like how long you want your target to be. In our case, it's just 1, because we're just trying to predict 1 day in the future. And our batch size is also important here. Make sure that your batch size is something reasonable, something that you can get a lot of iterations in on your model. I think this one allows us to get 75 iterations per epoch, which is pretty good. Yeah, we just add that to our window generator function. Okay, and now we create these properties that allow us to get the train variable, the validation data frame, and the test data frame. And we are able to kind of understand, you know, like what each of these things do. So when we toss it into our model later, we don't have to define what our train, validation, and test data set are, and it allows it allows TensorFlow to just use whatever thing we put in as our data frames, and generate a randomly generated data set every time. Okay. So here we're basically, I'm creating this function so we don't have to do this every time we want to fit a model, where we just pass in what we want the layers of our model to be, and then we give it the window, or like the generator, like the window generator thing that we want, and we're able to change our patience. I don't think I change the patience that often, but if you wanted to, you can change the patience so like it doesn't stop as early, so you want it to go through more iterations before it realizes that it needs to stop. So what this does is, whenever, say, your validation loss doesn't sort of increase, or doesn't decrease per sort of epoch, it waits 2 before it doesn't increase. What's up, Adam? It doesn't sort of increase when you have this validation loss. So if it doesn't decrease whenever, sort of like after, so between between epochs, there's something called a validation loss. So you have like this loss, and then you have a validation loss. The validation loss is the data that your data set's never seen before. And if your validation loss doesn't go down between epochs, it will stop the thing because you're overfitting. Okay, and then this reduced learning rate on plateau will monitor the loss inside of your actual while you're running the model. And if if your model isn't, and if the loss of your model isn't changing very much, it will decrease the learning rate by a factor of 1/2 or 0.5. So it'll just decrease the learning rate until it gets to a reasonable learning rate. Okay. And now after this, we have this thing where you compile the model, and the loss function that we're using, that I decided to use, is mean squared error. If you're doing something like categories or something like that, you would use like cross categorical sort of categorical cross entropy or something like that, or like just straight up accuracy. But since this is a regression model, we're using mean squared error, and we're using the optimizer atom, and we're starting off at a low learning rate because we don't want it to go very fast, because we have a relatively small batch size, therefore our learning rate should be small. And then we're just keeping these extra metrics just to see how these metrics are stacking up over time. And then we just call the model.fit, where we have the window.train, which is this right here, where we just take the train data, and we have the model.val, where we just have the validation data, and then we add our callbacks, and we say how many epochs we want it to be. It's that easy. That's all you got to do. And then now if we wanted to like create a model, it's just as easy as saying we want the layers of our model to be this. So this is the model that I created here. Here, where there's a dense of 128, dense of 5, and the output of 5. And you're able to take this output, and so we use softmax on 5 for a regression normally, because it's softmax just gets like the map, like, so say you have like 128 different things for each 5 array, it just gets the maximum for each of these arrays. So it finds like it adds all of them up and then gets the maximum, like the softmax, and returns that. Pretty complicated. I probably shouldn't have talked about that because that might confuse people, but essentially you just have this model where you just flatten all the things. So it turns out, so it goes from being like this batch, like however many are in your batch, and then be a 2D array of time and features, so like where you are on the time scale and features, and it returns a batch, and then a 1D array of time times of size time times features, where it just puts it all out into a single 1D array. And we reshape it at the end just because it was easier for me to redo that than it was for me to change the generator code. But you can see that our loss isn't too terrible. Our loss is only about, I don't know, 1.05, 1.03. I could actually run all this stuff really quick. The stream might lag, but small price to pay for salvation. Okay, we're just gonna go like this. So yeah, this will generate the plots. So we have more random plots, more plots just to see what it looks like. And boom, 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 boom. Okay, so here's this model generating. Our loss is a lot less. And you can see it's kind of generating this loss function, and whenever the validation or the loss of this function isn't increasing very much, it should decrease the learning rate or just stop entirely. So this decided to stop entirely. And we can see the summary of our data, where we can just see that the first flattened layer is 240 long, and then our hidden layer, our dense layer, is 128 big, and that's what is going to do all of the actual fitting on our data. Okay, and then at the end we just reshape it to fit because we needed it to be reshaped to this in order to calculate our loss function. And so these are our predictions. So let's see if I can run this. So these are our predictions from that model. You can see they're pretty close. They're not too bad. They create I'd say they create valuable sort of insight on what's going to happen to the stock eventually. So like you can see, like this one went up. These two are very close. This one went up for some reason, but it's whatever. This one went up too. This one, yeah. So you can see that these predictions are not too bad already, but we're going to get much better predictions come later, and then we can just change the actual column that's being produced. So this one's the close, but if you wanted to see say the open of the, plot the actual labels that it created for the open values of these, you can see we can predict again these values for the open, so it predicts all these different values the entire time. Okay, so that was a many to one relationship. We're going to talk more about many to one relationships in how convolutions do it. So basically we have this convolution width. So we kind of talked about this before. This was on the slides. This input is only 5 long and it creates 1 output, and we're able to create this thing where it has a convolution for each of these windows here. So you can see all these different windows of how these stocks are being generated, and you can run this. Let's see if I can get this going. Okay, yeah, so if you run this, we can so what I did here, instead of having one hidden layer, we now have multiple hidden layers, which I'm gonna show you guys a video of how multiple hidden layers make a difference on predictions. And you can see here in this YouTube watch thing here, we can kind of look and see how this data is being fit to the graph. So this is one of my favorite YouTubers, Dex. He does a thing called neural networks from scratch, where he's showing you. So these are 2 neural networks in a sequential. So these are 2 different layers being changing the way this graph, so the regression line looks. So you can see, you can pretty much do whatever you want with this line in the regression area. So this is an example of a rectified linear unit, but you can see all this stuff. Yeah, pretty cool. But if we have say multiple layers of these, and we wanted to fit a function like this, like a random function, I think this looks kind of like a cosine function. It'll fit this data, so it works almost like it can fit almost anything. Neural networks are very versatile, and it allows them to kind of fit any type of line that you want over time that you pretty much need. And yeah, so if you look here, this is the actual line that it's producing, and then for each individual node, and then this is what the whole sum of the nodes looks like. I thought this was a really cool example of how neural networks work. You can kind of see how it's changing all these functions to work exactly how it's supposed to with this graph. And yeah, so this could be any type of function. And this is basically what we're doing here, is we're adding 2 different layers, and we're trying to fit these layers into its own graph. And yeah, so that's why there's 2 hidden layers here. It allows them to fit nonlinear functions. So I thought that was pretty cool. I probably shouldn't run this because the stream might stop, but you can see that the loss is a lot less than it was before. Let me see how much different it is. Oh, so the one we did before had a lot more inputs, but if we have a lot less inputs and we have a nonlinear function, like the loss is about the same, which is pretty cool. So let's go down. Right down, let's see where this is at. Oh, it stopped. Yeah, so you can see this convolution window. So with only 5, it's still giving back okay predictions. This is not a very good example, but you can see like there's some reasonable data here. Like this goes down a little bit, this goes up a little bit. It's really good for good loss score right there. It's an okay loss score because this loss score is it's between like 1 or 2 days, so it's an okay loss score. We're gonna get a lot better loss score later when we go into convolutions and long short-term memory or LSTM models. But we can see here, like this is another way that you can do a convolution, is to have instead of having like these all be all produce one output, so like having a bunch of inputs produce one output. Say if we have like a conv window, let's see if this can print out. So instead of doing multiple dense layers, we can create this thing called a convolution in there, convolution 1D, and create like 64 times 5 filters. So it produces like 64 times 5, 240 filters. Is that right? Well, we gotta wait for this anyways. 320, my bad. 320 filters, just for the open, high, low, close portion of this, and it fits this data fairly well. You can see the summary. Yeah, it creates 320 filters based off of this data, and it outputs dense of 320. So like these dents are like a regression for each of those different things. So each individual open, high, low, close has its own convolution of 320 different convolutions, which is pretty crazy. And these get a lot closer. So these start getting really close to how it's supposed to look. So as you can see, these are a little bit more accurate than they were before, but we're still not done. There's still a lot more we can do. If we wanted, say, a wider window, we wanted to add more data to this convolutional neural network, we can say add convolution and then also a dense hidden layer, and then output this dense hidden layer. So what's happening here is we're permuting, we're switching the actual thing. So we're switching it from being the first part of it, time, and then features, to being features and then filters. And then what we're doing here is we're saying that this is going to become batch features filters to batch time filters. So we're basically converting it. Wait, no. Batch time features. Batch features filters. Wait, no. And then this is going to be time filters, and then this is going to be filters, and this is going to be time. Okay, so while that's running, I might be lagging. I'm sorry. My computer's going ham right now. I probably should have given it like a certain amount of resources, but it's fine. It doesn't really matter all that much. Yeah, we look at the summary. You can see that we stay the same time, and all we're doing is just creating a convolution for each of these the time and data attributes, and we're able now to get a really, I would say, fairly accurate representation of what the stock data is actually doing. So this is, again, every time it predicts one of these, it's only seen this at this input. So it predicts. So for this prediction right here, this prediction, it's only seen this input. In this prediction, it's only seen this input. So it does this kind of like warm-up thing where it like warms up, and then your final prediction is going to be like, you know, the actual prediction that you want. And you can see that these are much closer than before. Okay. So let's go back to our slides. Okay, so we have this one, this one, this one. So we talked about that. Oh, I should have come back. So this was the many-to-many thing that I was talking about before, where it creates this many-to-many relationship between, it takes in a bunch of the inputs, and then it runs a function on all those inputs and generates like the whatever specific output you want. A really good use for this would be like translating languages or summarizing books, or something else that's really useful for this would be like stock market analysis. Didn't think of that one. And many different things where you just have a many-to-many relationship, and each individual thing that it tries to translate is correlated to some other thing and is also reliant on the things before it, or like is on some sort of sequence where there's like a T that it follows. Oh shoot, let me go back. So this is the single shot. We're really good at making categorical predictions. So let's go back. So the single shot is actually this one. Oh wait, no, the single shot is this one, sorry. No, the single shot is this one because it just takes in a bunch of inputs and then it outputs a bunch of outputs. So an example of single shot would be, where is it? Here. So this multi-step here, oh yeah, I forgot to do this. This multi-step here takes in like a bunch of different sort of inputs based off of where like the past, and then it produces pretty much the same amount of predictions. So if we were to recreate this in our stock data stuff, it would be right here, where we have again our batch time features 64, 24 for our time, so like that's our time, that's our T, and then 5 are features are open, high, low, close. And then these predictions, instead of it being, so these 24 predictions are like 0 through 23, and then these 24 are 24 through 47 because we shifted 24 in our generator. Okay. So let's go back here. Okay, so we have this, and then now we can do this. So we can take this lambda where, so this is just taking one feature. So this is an example of, so this is my example of the one-to-many, where it only gets the first portion of that, of each of these features, and it tries to generate a model. Later on we'll do it so it gets an actual convolution width instead of the instead of just the first one. Okay. Okay, did this run? Is this running? Oh, it's running. Okay, it already ran. Okay. Again, this one's not extremely complicated because it's really, all we're doing is we're just creating multiple dense layers, and then these multiple dense layers come out with essentially what is a non-linear, it's just like a line that's going to be the same for all of them. Like this line doesn't change much between layers because it's regression, and it didn't go over many sort of different, it didn't go over many of the different epochs, so it doesn't have much variation between steps. Okay, and so here's an example of if we were to generate stuff for the actual, why is my stream lagging? Is my stream lagging for you guys? Open interest defines the total number of open. Oh, okay. Interesting. Yeah. No for me. Okay, that's good. And then here's the. Okay, so this model was trained, and then this is the Lstm one. So here's the convolutional model that it's predicting. You can see it's also going to be the same. I honestly don't know what's going on. why it's being like this, but I will change the code later and try and figure it out, because I'm still kind of learning this stuff too. It's pretty complicated. It's pretty complicated stuff, but I'm going to go back, since we don't have much time, I'm going to talk about recurrent neural networks and what that means. And basically what a recurrent neural network means is that it's a way to fit functions that are recursive. So say you have like something whose output is dependent on what its input, or like what its past input is, or has some sort of sequential data. So like say you have like an image, if it's sequential and like where the sort of place it is in the data matters for what its meaning is, RNNs are very useful for that, because it allows you to store states and basically use these past states in order to produce a new state, and basically have try and generate ways to fit recursive functions, which is really useful. And recursive functions are everywhere. If you guys like really think about it, like the definition of a recursive function is like saying that like you have like this past state. So like having like, so for example, if you have like a y and you have this like constant times the inputs, this y, like the output y, or the new state, is dependent on the old state of how that works. So basically it's like remembering these sort of sequences that it's happened before, and we'll talk about how we can make this a little bit more efficient, because right now if you were to do backpropagation on this, which is a huge topic, basically you would have to redo all the fits backwards. So you have to find the parameters w that fit for the entire sequence every single time. So this old state here, this ht1 is sent into this a recurrent neural network and is weighted. So like these weights are weighted on h and on x, and then it creates this new h and it produces an output h of t, which is then that state is sent back into the function. So it's just a way to model like recursive functions and stuff. So yeah, here's another way. This is from the lectures, Stanford lectures. Essentially, yeah, so we have this function that fits a tanh function, and it calculates this weight w based off of, you know, the past state and what inputs you're sending into it. And these inputs in our case are the past stock data. And this output is basically just determined, you know, the actual y of t is just after this weight matrix is calculated. You just calculate your y of t by taking the state that it generated and multiplying it by your weight matrix. So here's what it kind of looks like in a visual way, where you have, this is like if you had one network, so you have like a sort of initial state where like h of 0 is all zeros, and then you create this function w that fits all the inputs from x1, and then it generates out an h1, and then that h1 is sent into the next function. So that state, instead of it being all zeros, that h1 is a state that is sent to the next function, and then that function generates an h2, etc., and which goes to h3, ht, etc. So these recurrent neural networks all are multiplied by the same weight matrix, and this weight matrix takes a lot of calculations to solve for this weight matrix, which is we'll get back. We'll talk about that later. So just the idea is that you have this one weight matrix that's being generated from a recursive function, and then you're basically trying to find like the constants in like the recursive function. And so when we have all these functions, we can generate a many-to-many relationship through a recurrent neural network via just generating a y for each of these states, and then computing the loss function for each of these, and then summing all the losses. Okay. So after you've done that, where you've computed all the different y's, you can also do a many-to-one relationship where you just compute the last output function, where you can create these states and do this weight matrix for the entirety of the actual function, and you can also, and then you just generate one y. So it regresses and generates one y. And yeah, so this is kind of what it looks like in the actual math. This thing. So the reason we like doing this is because we can just send like this function onto the stack and send it to our GPUs, which can do thousands times more calculations at the same time versus like a normal CPU, which is why GPUs are really good for stuff like LSTMs and transformers and stuff like that, because they can do a bunch of concurrent calculations. Okay, but there is a problem with this. So every time we go back, we have to recalculate this W. So this W is global, but every time we go back, we have to refit this tanh function. So the more, I guess, functions that we fit, or the more data that we fit, the more it grows exponentially, the amount of calculations required to calculate the weights for a recurrent neural network. And this is called something called an exploding gradient. And you can also have something called a vanishing gradient, where you don't keep enough of this gradient. And so basically somebody in like 1999 created this thing called an Lstm model that was proposed to fix this problem. And in Lstm, it's basically the same as an RNN, but instead of having to calculate the weight matrix every time, you create this thing where you have this new matrix that creates this, that has these properties where C of t is like the actual how much it's being weighted, and H of t is like where your current state is, or whatever. No, H of t is like your current sort of input. So yeah, now these LSTM gates, I'm gonna go over this quick because I've already run out of time. But these LSTM gates, there's four main gates. There's the input gate that says whether or not to write the cell. That would be 0 or 1. The forget gate would be whether to erase the cell, or like whether to forget the actual thing that's inside of the cell. And that's whether to erase the cell. The output gate is how much to reveal the cell, so that's between 0 and 1, and that's how much data we want to actually reveal from the cell. And then we have the gate, which is how much we want to write the cell, which is, instead of it being a sigmoid, basically it being 0 or 1, it is a tanh function, so it's an actual fit function that has like a value 0 or 0 between -1 and 1, and this is like the actual value that we want to remember. And then we have this long short-term memory, all this stuff. So if you guys want, I can go over this more later. But yeah, basically the idea is that LSTMs allow you to capture the gradient in a very in a much faster way, so it's easier for the computer to compute these values. So like it's almost, I would say, like 200 times faster for your computer to calculate a long short-term memory matrix than it is actual recurrent neural network, just because it's just so much faster. Yeah, because instead you don't have to calculate W every time. You have to just calculate like the one constant. Okay, so let me just go over the code. Essentially, all you have to do is just, so the reason I'm permuting this is because I want to run the LSTM over time. And so I'm basically just switching the time and features, and then I'm running this LSTM with 256 different different ones of these matrix. So the LSTM, the actual LSTM matrix here is the IFOG. So we're making 256 of those matrices where it says whether or not to input, forget, output, and like what actual value you want to forget or sort of send to the next function. Yeah, so basically we have this, we are able to fit these losses and get something fairly close to what we want, and we can see that it's moving a little bit more. Again, I'm still kind of learning this stuff, so hopefully if you guys want, you can go in here and change all these options and figure out, you know, what works best for this model. But I didn't have time just because it takes a while to run all these models, and I had to research how I had to actually learn what an LSTM was, so we don't speak about that. But yeah, essentially all it is now is we are able to see the model do its thing, and this is how the LSTM model came out, and the loss function is really good. So yeah, so now we're getting losses of like 0.0020, 0.0018, 0.0017, and it's looking really good. So this is what our LSTM looks like. And yeah, hopefully you guys enjoyed this. I wish I had a little bit more time to talk about this, and I'm sorry that it took me so long to come out with this presentation, but hopefully you guys all were able to sort of understand what's going on, and I will be posting resources for much better explanations than I could explain all this stuff later on in the Discord. So thank you guys for watching, and I hope you all have an awesome day. Bye.